All right, today we're going to talk about polynomials. Polynomial functions. Okay, so what are polynomials? These are the kind of functions that we've seen all the time, and it's kind of interesting to first introduce them because I feel like there's no real clear-cut way of doing so. But one way is to explain just by function notation what a polynomial function looks like. So we say a polynomial has this form, right? P of x. We call a function, normally we denote P as a name for the polynomial function. And then we write it this way: a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a sub 2 x squared plus a sub 1 x plus a sub 0. So this looks kind of, maybe to some, might seem a little bit intimidating because you have not only exponents, you also have little subscripts. So this is just a general way of expressing a polynomial. So this is just a general, the general form of a polynomial. Polynomial function. And the important things about the polynomial we will discuss shortly. But sometimes it's good just to give you an example, just an example of what a polynomial looks like. And then hopefully you'll see why we write it in the above form. So actually, quadratic functions are also polynomials. So if I write a polynomial like this, x squared plus 5x plus 6, for example, we all know that this is a quadratic function because of the x squared term. It's the highest, it's the exponent with the highest power. But also this function belongs to the polynomial function family. So not only is this a quadratic, it is also a polynomial function. And then the question becomes, how come? Why is that? Well, there's certain things that make a polynomial, and for those very same reasons, if you don't have those conditions that are met, then you're not considered a polynomial. So one thing is that we have what are called coefficients, right? So all of these a values here that you see, these are all coefficients. So the first thing I want to say is that we have coefficients. So the coefficients a sub n, so we say a sub n as saying a subscript n. So a sub n minus 1, all the way down to a sub 2, a sub 1, and a sub 0. They're all real numbers. The coefficients a sub n all the way to a sub 0, or a nod, are all real numbers. So for example, here, what are the different coefficients here? They're all real numbers, right? So that checks off. Then the next thing, and probably the most important thing, is that the exponents for each term is or are are all non-negative integers. This is an extremely important phrase or terminology. They're non-negative, meaning that they can't be negative, but they could be what? They could be 0 or positive. That's what that means, right? Non-negative. So also equivalently, we can say it could be 0 or positive. And when we say integers, right, we know that we mean that they're whole numbers, but we only want the positive ones or 0. So if that's the case, if they're integers, then what can't they be? Can anybody tell me what can't they be if they have to be integers? So first of all, they can't be negative. The exponents can't be negative. And they also can't be what? Decimals, right? Technically, yeah, there's many decimals that it can't be. It can't be fractions, right? It can't be fractions. And it can't be anything strange like irrational numbers. Very good, Chen. That's right. So it can't be those things. The moment you see that, then it's not a polynomial. So sometimes it's good to understand what something is by understanding what the opposite or what it isn't, right? So then what would be an example of a non-polynomial? So maybe we can call this a non-example. So if I have a function like this, so far let's write 3x to the 4th plus 5x squared. And then the moment we have something like 3x to the negative 2, this is not polynomial. You see that? This is not a polynomial. Well, why is that? It's because the negative 2. This is what? A negative integer as an exponent. Because it has a negative integer, it invalidates itself being a polynomial because a polynomial must have non-negative integers as powers or as exponents. So that's the idea. So you can only have positive or it could be the 0 value of a exponent. But you can't have anything fraction. You can't have any half or third or 3/4. You can't express any fractional exponent, and you can't have any negative exponent. And so that's what makes a polynomial, and that's what would not make it into a polynomial. Okay, so is that clear to everybody so far? What's going on? What things are polynomials and what aren't? Again, these are simple examples of one being a polynomial and the other one being not a polynomial. And now let's go back to this form that we have here for a polynomial. Let me just see the chat. Yes, everyone's good. Okay. So from here, we have several things that we always want to be able to notice and identify. One of the most important things from any polynomial is the following. So these are like important aspects of a polynomial. Okay, so I'm just gonna copy this again. I kind of just introduced this really quick. I'm gonna bring it down here. And I'm gonna erase this a bit around. Okay, so what do we care about the polynomial of any given polynomial that we're given? The first thing is to notice, well, yeah, one thing we notice is that normally we write polynomials with the highest power first and every power that's less than it afterwards. So we write in descending order. So normally polynomials are written, just a little note here, note, polynomials are written in descending order with respect to the power or the exponent. So the highest power is first, right? This is going to be the largest or highest power. And then as you see, n minus 1 is 1 less than it, and then 2, and then 1, and then this is really to the 0th power. But you go all the way down, right? So this is descending order. So the exponents are descending. Okay? So that's normally the way we write it. If you write it in another jumbled up order, it's still the same polynomial. It's just that conventionally we write it this way. Okay, so the highest power, the largest power, has a very specific name, and that name is called the degree. So the degree of a polynomial is the largest power. And that's one thing we always want to be able to spot and identify, because it'll give us a lot of information about the graph of the polynomial. So the degree is the highest power. And so if you go back to our example of a quadratic function, which is also a polynomial, the highest power is what? What would be the degree of a quadratic function? 2. That's right. That's as simple as it is, guys. We literally look at the polynomial and we say, what's the highest power? Well, here, obviously, it's 2. So that would be my degree. That's it. So this is my degree. And this notion of knowing what the degree is, like I said, gives you a lot of information about the graph and about the polynomial itself. So that's the first thing we care about, okay? We care about the degree. We also care about, next to it, is the, well, let me move this a bit here. The term that has the highest degree, that term is called the leading term. So the leading term has the highest power. So the term is the entire monomial here, as we call them, with the base along with the coefficient. So that's the second thing we consider, the leading term. So this contains the degree, Alongside with that, we care about the coefficient. We care about our coefficient. So what is our coefficient? We call this the leading coefficient. That's number 3. So the leading coefficient is the coefficient of the leading term. So that's how the word leading comes into play. Right? So we really care about this leading term because it really influences a lot of what the graph will look like. And then we also have at the end, at the very end, we have this a sub naught here, right? Here, this is known as our constant term. This is the number that just is not paired with any other variable. So that's pretty much what we like to highlight when we have a given polynomial. We should be able to spot the degree. We should be able, from there, understand the leading term and then the leading coefficient, and also look at the constant term. We like to note what these values are from a glance of the polynomial. Okay? Okay. So let me see one thing. So I'm gonna post something onto Google Classroom under lecture number 9 material. So for those of you who are able to open up your Google Classroom, under lecture number 9, there's a PDF file, and I want you to see if you can open it up. If you can't, it's okay. We're still gonna go through it here. So I'm gonna open it up, okay? And let's see, where is it? Yeah. All right. So so you can put your name on there, of course, the date. And then here we have you know, some vocabulary that we've just discussed. So just to help you guys out a little bit. So we haven't really touched the last two yet. We're gonna get there eventually. Is leading coefficient and leading term the same? I think leading coefficient. Yeah. Okay. So that's a good question, Jen. It's connected. They're related. Just and so hopefully with some of the examples, you start to see how they're distinguished. What's the distinct? How do we distinguish between the two terms or phrases? So leading term is the entire it's the entire term that contains the largest degree. The leading coefficient is just the number, like I think Gabriel said, it's the number or the coefficient that's part of the leading term. So the leading term is the bigger part, and then the leading coefficient is part of it, part of that. Okay, does that make sense? Okay, good. So then let's go here to this. So the degree of the polynomial is obviously the highest, largest. I don't know sometimes which words is better. The largest power exponent among the terms, right? So we established that already. And then the leading term or coefficient is the term with the largest power. And that's the leading term, and the leading coefficient is the coefficient of the leading term. And the constant term is just the number without, or seen without the variable. It's just by itself, right? So again, we just discussed this. So let's look at an example of a polynomial. As you can tell, p of x, right, is negative 2x to the fourth plus 5x cubed plus 4x minus 7. So we should quickly be able to fill all of these blanks. As you can tell, why is this a polynomial? Well, we have all these smaller terms, right? And all their exponents are non-negative powers. And of course, whenever you have a negative 7, you can think of this as being x to the 0th power, but we know x to the 0th power would be equal to 1, right? So we don't really see it there, but we can think about it that's there hidden. So then what would be the degree of the polynomial? It's pretty easy to spot, right? 4, 4, 4. Yeah, that's right. It's very easy to spot. The highest exponent here is 4. So then what do we say? The degree is 4. So we haven't really talked about the name of a polynomial. So we'll skip that just for now. And then what's the leading term? And now, Chen, hopefully you see the difference now. What is the leading term? Remember, it's everything that's included with the highest power. That's right, Chen. So the leading term is negative 2x to the fourth. So it's negative 2x to the fourth. That's right. Now, what's the leading coefficient? Well, then it's going to be the coefficient of the leading term. And so then we'd say it's going to be negative 2. No x. There's no x to it. It's just negative 2. Coefficient is just the number. There's no variable involved. And then what's the constant term? Well, the constant term is going to be the number that's by itself, just constant there, you know? So that's going to be negative 7. Okay. Is this straightforward, guys? Is this clear? There's no real like trick here. There's no, you know. Thank you. There's a lot of yeses. Well, yeah, I'm glad Felipe is starting to make sense. Yeah, so these are just ways to describe our polynomial, okay? These are names to describe. Okay, so what is the name, or how do we name polynomials? So sure, the polynomial it's associated to p of x, right? But we're gonna be more specific in how we name them. And the way we name a polynomial has everything to do with the degree. So the degree is like a way of naming this polynomial, or I should say categorizing this polynomial. So there's going to be two kinds of labels or names that we have for this polynomial, and it has to do with the degree. So one way to describe or to name this polynomial is by saying this is a fourth degree polynomial. I'm just going to write poly for short. This is a fourth degree polynomial. That's one way of labeling this. And it strictly comes from the degree. It comes from nothing else. But fourth degree polynomials also have another, I guess you can say, a moniker. And we call them quartic polynomials. And of course, as you continue on with the exponents, right? Fifth degree polynomial, sixth degree polynomial, then those names kind of, I don't know. I don't know if we have specific names for those. But for example, if it's a third degree polynomial, we call them cubic polynomials. If it's a second degree polynomial, we call them quadratics. You see what I mean? If it's a first degree polynomial, they're also known as linear. We don't really say linear polynomials, but it's you can say linear functions of sorts, right? So it has everything to do with degree. That's it. That's really the main thing. So if you know the degree, you know a lot of information about the polynomial. Okay? So let's go to the next one. Now, what do we have here? The highest degree, now it's going to be quicker and quicker, right? It's going to be like clockwork. The highest degree is 5. That's simple. And then the name of the polynomial would be what? This is a fifth degree, right? It's a fifth degree polynomial. That's right. So this is a fifth degree polynomial. And actually, there's also a name for fifth degree polynomials that we use. And they're, I don't know if I'm saying it right, because quintic polynomials. because they're fifth degree. So it has everything to do, like I said, with the degree. What's the leading term? It's the term with what? 3x to the fifth. You see, you guys are too good, too quick, learn too fast. This is quick now, right? Now we're not even like sweating it. Leading coefficient is 3. It's too easy. And then the constant term. Let's see if we all got the constant term here. 0. See, nothing escapes you guys. 0. We don't see it because we don't have it. In a way, we have to just say, hey, there's a 0 there. Because if we add by 0, it's really adding by nothing. So we can disregard it. But in a way, it's there, you know, plus 0. So that's the constant term. All right. Are we good with this? Feeling good about this? Feeling good about identifying polynomials, being able to decipher, break down the information from the polynomial that we're given. Okay, great. I'm glad this part is straightforward because it is. All right, so now you see those two things that we haven't defined yet, the zeros of a polynomial and the end behavior. So we're going to head it towards that aspect of the polynomial. And first we're going to consider, so I'm going to add a page between here. We're going to be talking about end behavior. Okay, so that's something maybe to some you haven't seen before, or maybe you have. End behavior. This sounds a little strange, right? End behavior. You're like, wait, what do we mean by behavior of a function? What does that even entail? And what about the ends? So simply, we're just going to be considering if we were to graph a function that's a polynomial function, we want to figure out, or we want to know, or we want to determine what happens to the graph of such a polynomial when we look at the extremes or at the ends, whether it be to positive infinity side of x values or the negative infinity side of the x values. So it's like saying this. So just a simple example, right? Let's say I have a polynomial. And one thing about polynomials that you start to see is that polynomials are very quote unquote nice functions because they're all connected. It's always going to be connected, and they're labeled also as smooth. They're smooth. There's no jaggedness to it. There's no like any funny business going on. So whenever you see something like this of this sort, right? It would most likely be some kind of polynomial. Now, eventually, we'll start to figure out what kind of degree this polynomial is, what kind of leading coefficient it has, and so on. So these arrows indicate a lot to us. These arrows here indicate the following. If I continue on, that's one limitation we have with graphing, right? We can't graph the entire function. We just say, hey, this is what happens. These are little arrows here that indicate the direction. So as you approach the x values, as you approach the x values, and as the x values get larger and larger, so as you move to the right, what happens to our function? What happens to the graph of our function? Based upon this graph, we say that it keeps on going up and up and up. So that's part of their end behavior. That's the behavior of the graph at the right end of the graph. And then we ask ourselves, what happens at the left end? What happens when my x values go to the left towards negative infinity? We look at our graph and say, oh, it looks like it's going to be going downward, right? To negative, the y values. So it's going to be related to the y values. The y values here of this graph seem to be going to negative infinity as the x values go to negative infinity. So then how do we express end behavior? So the end behavior of this graph, so let's say if I call this y equals p of x, right? The end behavior can be expressed as the following. We say two statements. It's really a two statement. It's a two statement explanation. One says, so if, I should say not if, I should say as the x values, and so we're going to use this little notation here with the arrow, as x, and this arrow means approaches or gets close to. So as x approaches infinity, the y does what? What do the y values do here? It also approaches what? Yes, Chen. So when we say increase, we're increasing to what value? Well, this value is not really specified, but we know it gets increasingly larger and larger, and we call it infinity. That's it. That's the first statement for our end behavior. As x approaches infinity, y approaches infinity. And then what happens on the other end? As x approaches negative infinity, y will approach negative infinity. That's the second statement. And we have just expressed the end behavior. So again, we care about what happens at the right end, I guess you can say, right? The right end. And we care what happens at the left end. The right end is denoted by my x values going to infinity, positive, and the left end is denoted by my x values approaching negative infinity. So end behavior is just a way to express what we see in so what we see from the graph. We're just expressing them in more symbolic language. So we can say we can express end behavior just with words, saying, oh, as x goes to the right, as you move to the right, your function keeps on going up. That's one way to express it in words. But notationally, symbolically speaking, we say the same exact thing just with symbols. We say x approaches infinity means the same thing as saying as you move to the right. So as you move to the right, my function goes up. Or in other words, my y values go to infinity. Do you see how they're expressing the same thing? So we have to learn how to express ourselves, I guess you can say mathematically speaking. So is that clear? Somewhat? Okay. Now, so that's just like a little introduction, right? A little like example. But eventually we'll be given a polynomial, and we're going to have to be able to determine the end behavior without even graphing it, just by looking at the polynomial. So in order to do that, we need more info. So I guess we can start with another example. What if I have the polynomial? So let's start with something really small, x squared, right? We all know what x squared looks like, hopefully. Pretty sure we all do. We talked about it last time, right? It's a quadratic. Can anybody tell me what's the end behavior? So remember, we need the first statement and the second statement. So as x approaches infinity, as x approaches negative infinity, y approaches what? And what does y approach? Can anybody tell me it approaches what? Just by looking at the graph. Right. It approaches infinity. And it approaches infinity on both ends, right? We know this to be true. Okay, so that was a quick one. Let me give you another one. What if I have the polynomial negative x squared? What is this going to look like? What does this look like? Well, remember negative, that negative here is a transformation, right? It's a reflection. So then it will be just reflecting the parent function x squared. So we got something like this, right? Don't we? And then the end behavior also seems pretty simple. To express. So we say as x goes to infinity, my y values move towards negative infinity. And as x approaches infinity, the y values move towards negative infinity as well. Simple enough, right? We're just looking at the graph. So does this make sense? The end behavior is quite apparent, right? For these. Okay, and then I'll give you two more, and then we'll try to see a more of a what's the general idea behind all this. What if I have x cubed instead? What about x cubed? Well, x cubed looks something like this. It's like a windy curve here. So what's my end behavior? I'm gonna eventually just abbreviate end behavior. So one is what? As x goes to infinity, y goes to not negative, but positive infinity. And as x values approach negative infinity, this is a lot of negative infinities. And then y goes to negative infinity. Makes sense? So as I move to the right for the x values, my y values move towards infinity, positive. And if my x values move in the negative direction, then my y values also move to the negative direction. Is that clear as well? Okay. And so let me give you one more of these. I'll put it right here, actually. What happens if I were to reflect that function? What happens to it, the end behavior? And what happens to the graph? Well, it's just flipped across the x-axis. And then my end behavior, as x goes to infinity, y goes to negative infinity. And as x goes to negative infinity to the left, as x goes to the, as your x values move to the left, your y values move positive infinity. And you may ask me, why do we do all of this? Why? Why these? Why start with these small polynomial power functions with these exponents, these degrees? Is because if you know these, if you know the end behavior for these four functions, you essentially know the end behavior for any polynomial. Because the end behavior of any polynomial is summarized in these four different kinds of end behavior. There's no other way to express end behavior once you know these four. These are all the possible ways that the end behavior can occur for any polynomial. And we'll see why. But before we continue, I want to go back to this real quick and just see two things. I need two things here. I need to know the degree, and I need to know the leading coefficient. And I'm going to call the leading coefficient LC, okay? Just to abbreviate. So what is the degree for x squared? The degree is 2, right? Okay. So we know that. But what we're going to care about more is the parity, P-A-R-I-T-Y, of the degree, which is whether it's even or odd. So obviously, the degree here is going to be even. Now, what's the leading coefficient of this term? It's obviously what? 1. But what we're going to care about is not whether it's what the number is. We're going to care about if it's positive or negative. So obviously, the leading coefficient is going to be what? Positive. And we're going to do this for every single one of these. So you see, the degree is going to tell us a lot about the end behavior. And not only the degree in tandem with the leading coefficient tells us what end behavior it will result in. So the degree here is also even, but the leading coefficient is what? Negative. And the degree here is what? It's odd. Yeah, it is 3, but we care more about the fact that it's odd more than the fact that it's 3. So the degree is odd, and what's the leading coefficient? Positive, right? And then lastly, the degree here is what? Still odd, but the leading coefficient is negative. Now that's this here, this is going to be the important thing from now on. Because you can categorize any polynomial with one of these pairings. So any polynomial, the degree has to be either even or odd. And for any polynomial, the leading coefficient has to be either positive or negative. So when it falls into one of these categories, immediately the end behavior is given. Now, the question is going to be, how come? How come? How is it that any polynomial will fall into one of these pairings, right, of degree and leading coefficient, and the end behavior will be exactly the same as one of these smaller, very simple and basic polynomials? How come? How come that's the case? Well, like I said, it has everything to do with the leading term. And we're looking at the ends. We're not really considering or caring about what happens in the middle. So there's definitely a lot of different polynomials that can look very, hilly and have a lot of hills and valleys in them when you graph them. But what we care about are at the ends. We don't care about what happens in the middle for now when we talk about end behavior. So the end behavior of any polynomial actually does coincide with one of these 4 end behaviors. So like if you give me, for example, something crazy like P of X is X to the 100th plus 5X to the 98 or 87, right? Whatever. Something crazy like this, right? You may be like, that's a crazy function to graph, but I tell you, all I really need is the leading term. And I know for a fact that it's gonna appear the end behavior will be one of these four. So then based upon that, what would be the end behavior of such a function like this? Well, first thing I need to know is what? The degree. And the next thing I need to know is what? The leading coefficient, right? But again, for the end behavior, I don't really need to know specifically the number. I just need to know whether the degree is odd or even. And I need to know not the specific number for the leading coefficient. I just need to know whether it's positive or negative. So this is odd or even, and this is positive or negative. That's all I need. So then from this just made up example, what would be the degree, odd or even? Obviously it's even because 100. 100 is an even number. And then what would be the leading coefficient? Positive. That was easy. And now what? What's the end behavior? I didn't even graph this. You see that? I didn't even graph it, but I already know the end behavior. I know how the story ends. So for polynomials that have an even degree and the leading coefficient, it's going to look like what? It's going to look like exactly at the end, it's going to look like two graphs, the graph where at the both ends it goes up. So what do I say? 1. I say this, 1. As x goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to infinity. Done. End behavior taken care of. Does everybody understand what I'm trying to get at? I'm trying to get at the fact that any polynomial would give me has one of those four possible end behavior. That's it. There's no other possibility that we even need to consider. So let me see something real quick. Just give me 1 second. Do you guys see this? You guys seeing this, right? The diagram. Okay. I'm gonna see if I'm gonna try to graph this function. Wait, what was it again? It was 5 to the 87 plus x squared. Okay. So it's 5x to the 87 plus x plus 2. So see, look. Well, this looks really strange, right? I don't even know why it does that. Like, look at this. This is a weird polynomial. But again, what do I care about? What do I care about? I care about the ends, right? I don't care about what happens necessarily inside, in between. I don't really care. Hold on, let me see if I can. At the ends, right? At the ends is what I care about. Well, this looks very narrow, but it looks like what? It looks like, so what if I write x squared? Again, I only care about the ends. At the ends, whether I be on the right or on the left, they're both going up. So that's it. And look how crazy this function is. X to the 100, that's what? And then x to the 87. That's something we don't really touch that much, right? But it's just to give you, it's just to make the point. I'm just trying to make the point that I don't care how crazy the polynomial can get. It will always be one of those four possibilities. So that's it. Is that clear? Does that make sense? So let me quickly just summarize this, and then we can see this in action. So I like breaking it up this way. So this is my end behavior. My end behavior table. Okay, so we're gonna have some table divided. We have 2 columns and 2 rows. Okay, and so this first, the rows though, the rows will all be based upon so this is going to be based upon 2 things. The degree, I'm gonna try to write it this way. So this is the degree of poly, and this will be the leading coefficient. So if I have a even versus an odd, so if this is odd, this is even, and this is positive or negative. I only have 4 possibilities, like I said, right? So either I say the following. I say as x goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to infinity. But if I have a negative coefficient, but still an even degree polynomial, as x goes to infinity, y goes to negative infinity. As x goes to negative infinity, y goes to negative infinity. So then what you should remember is x squared. And again, things can happen here. Things can happen. But what I care about are the endpoints. So you can think about it as you have so for even degree polynomials, the end behavior coincides with the other side. So if you're even and you're positive, you both go up. If you're even and negative, you both go down. So that's the idea. Again, we care about the ends. Anything can happen in between. Anything can happen. But we only care about the ends. Okay? So again, we're just summarizing what we've just done. And then as x goes to negative infinity, pardon me, I should go positive infinity, y goes to positive infinity. As x goes to negative infinity, y goes to negative infinity. So then this is the case where we have the ends. So people do this a lot. So this is when anything can happen in between, but we know for a fact at the ends, one of them goes to the right as you go to the right, and the other one goes to the left as you go to the left. I mean, it goes up as you go to the right, and it goes down as you go to the left. Very similarly to what? To x cubed. And then when you have a negative coefficient, but odd degree, it's just flips. That's all. This is y, this is x. This goes this way, this goes that way. And we have everything we need to know for end behavior. So as x goes to infinity, y goes to negative infinity. As x goes to negative infinity, y goes to positive infinity. And that's it. Great. Any questions about this? Is this clear? Do we understand end behavior? Do we understand how how we're able to categorize any polynomial just given the degree of the polynomial and the leading coefficient, whether the degree is even or odd, or whether the leading coefficient is positive or negative? If you have those two pieces of information, you will always be able to figure out what end behavior is, what the end behavior will be, and it's one of these four, and that's it. Okay, so now that we have this groundwork set for before us, let's look at the next page of that file that I sent on Google Classroom. It's exactly on end behavior. So let's look at it. Now this should be 1, 2, 3, right? It should be quick. So the degree of the polynomial is what? 9. Odd or even? Obviously it's odd. What's the name of the polynomial? It's a 9th degree poly, right? What's the leading term? X to the 9th. So you guys are blazing through this. Leading coefficient is uno. But is it positive or negative? Positive. Okay, so see, right then and there, boom. Right then and there, odd, positive, end behavior. That's how quick it is. We already know what the end behavior is. And then what's the constant term? -5. All right, look, we filled it out very quickly. So the end behavior P of X is the same as what? It's the same as what function? The four that we've discussed. The x cubed, the x squared. What is it the same as if it's odd and positive? It's similar to, remember, there's only 4 of these. So which one of these 4 is the end behavior the same as? Right, it's x cubed. Which means that as x goes to infinity, so this will always be infinity, negative infinity, because we're saying one goes to the right, the other one goes to the left. Then y goes to infinity, but y as x goes to negative infinity goes to negative infinity. Good. And then we can, we can graph this something like this. It's just to give us an idea of the end behavior. Clear? So now the next one, same thing. The degree of the polynomial is what? 6. What is it? Even. What's the name of the polynomial? It's a 6th degree polynomial. What's the leading term? Negative x to the 6th. What's the leading coefficient? -1. If it's a positive or negative, it's negative. What's the constant term? It's +3. You see, now it's like clockwork, right? We're not even thinking anymore. We're just instinctively reacting to it. And then what is it similar to? If you have an even degree polynomial and its negative coefficient, it's the end behavior is the same as what function? One of those 4, negative x squared. That's right. We know what that looks like. So if we know what that looks like, then we know the end behavior for this one as well. X goes to infinity means that your y goes to negative infinity. As x goes to negative infinity, your y also goes to negative infinity because they both move in the same direction. So it's going to look something like this. And things can happen here, but we know that it's always pointing downward. Is this fun stuff or what? I hope you're having I hope you're having fun out there. It's a little fun. I'm glad. Okay. So we've talked about polynomials. We have an idea of what they are when you look at one with the function notation. We're able to now use this terminology about degree, leading term, leading coefficient. And in turn, now we're able to discuss end behavior, which has everything to do with the degree and the leading coefficient. So far, so good. Now, probably the most important thing about polynomials. One of the most important aspects of a polynomial, of any polynomial, are called the zeros. We care about what are called the zeros of polynomial functions. This is extremely important. We love the zeros. Does anybody know the word zeros? I'm glad, Felipe, you enjoy it. What are the zeros when I say the zeros of a function? That's good, Jen. Yeah, the x-intercepts. So there's actually several, I guess you can say synonyms for zeros. So one thing I can say is a zero, right? A zero of a polynomial a zero of a polynomial function is the x value whose y value is 0. So when we say 0, we're referring to the x value that if I were to plug it into the function gives me 0 as the y value. So for example, if I say let's start small with this. So if I say the function here, right, is like 5x minus 2, and this is a polynomial, first degree polynomial, it's a linear function. I want to say, what is the 0, right? What is the 0? What is the 0? What do we have to do? We have to set the function equal to 0. Why do we do that? Because that represents the y value, and I'm looking for the x value. So obviously, what would be the x value? 2/5. So x equals 2/5 is the 0 of f of x. Do you guys see that? Do you guys see that terminology? So we call the 0 the x value whose y value associated under this polynomial function is 0. And then someone says something very important. This 0, this x equals 2/5 in this example, would be exactly the place where it crosses the x-axis. So the 0 of a polynomial has more than one interpretation. So not only does the y value associated with the x value that's called the 0 is 0, this is also the place, because the y value is 0, this is exactly the point where it crosses the x-intercept, the x-axis. So it's called the x-intercept. So the 0 of a polynomial is actually synonymous with the x-intercept. And yeah, I'm gonna put an extra bar here. This just means like equivalent, right? It's equivalent. Not that they're exactly the same. So you can think of the 0 of a polynomial as the x-intercept. But there's actually another kind of interpretation as well. Maybe I should give you another example for that. What if I have the function, polynomial function, x² plus x minus 6. What would be the zeros? Here I had more than one. What are the zeros? What are the zeros? So what do you have to do for this, guys? Set it equal to 0 again, right? And then this is now a higher degree polynomial. This is a second degree polynomial, aka quadratic. So what do we do with the quadratics? We have to factor, correct? So this becomes what? X plus 3, x minus 2. And then from here, what do we get? X equals -3 and x equals +2, right? These are the what? The zeros. These are the zeros. But the interesting thing is not necessarily that they're the zeros, just that they're the zeros, is where do they come from? Where does x equals 2? Where does this come from? If you go backwards now, if you take a step backwards, the x minus 3 came from the fact, I know we skipped, we do these problems really quick. We skip, right? Because now we know what's going on. But it comes from the fact that what? It comes from the fact that x plus 3 equals 0. And it comes from the fact that x minus 2 equals 0. And you're like, okay, why do we care about that? What is x minus 2? What is x plus 3? These are the factors. This is a factor. These are the factors of the polynomial. Now, this is an extremely important connection to make. The zeros are associated with factors. So when you see x equals 2, you can't just see x equals 2. You have to see its factor, which is x minus 2. And when you see x equals -3 as a 0, you cannot just stay with x equals -3 as a 0. You have to see that it came from the factor x plus 3. That connection to establish, is essential when we talk about zeros of any polynomial. So, so here, if I say x equals a, right, as the 0, that means that the x-intercept is a comma 0. And this means that the factor, it means that the polynomial has a factor. And the factor is what? X minus a. This is probably the thing that may be new to some, but this is definitely what we want to emphasize. I want to emphasize this. And there's one more thing. People also call this, so we also say that x equals a is the solution of the polynomial when you set it equal to 0. This is just another way to interpret the 0. So all of these 4 different terminology, I guess you can say, they're all equivalent. So if you have this, you got this. If you got this, you got that. Like, they're all the same. Synonymously, we can take them all together. So that's one thing. It's a little about mathematics in general, is this idea of equivalence. And if you have one interpretation, you actually have all of these at the same time. Okay, so that's very important, guys. If you know the zeros, what do you know? You know the x-intercept. What do you know? You know that it has the factor and that it's a solution all at once. So this is important to highlight here. I tried my best with that. Yeah. Just Just give me 1 second. Let me see if I can. Guys, does this make sense? Is this understood? Okay. Okay. So if we know this, let's see if we can look at the next page. So now it's finding the zero. So see, now we're tagging along more stuff. We're tagging along more things and accumulating them as we go. So now not only do we, so now the beginning part is hopefully very straightforward, right? The degree of the polynomial, well, the degree of the polynomial is 3. The degree is an odd number, obviously. The name of the polynomial is a cubic polynomial or a third degree polynomial, either way. The leading term is x cubed. The leading coefficient is 1. It's positive. The constant term is negative, right? So that first part is now very simple. And because it's an odd degree and it's a positive leading coefficient, then I have something that looks very similar to what? X cubed, which means that as x goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to negative infinity. So all of that now we can do this in 30 seconds. Now we're going to get into the crux, the real meat of this, and it's the zeros. So how do you find the zeros? So the first thing is I need to set a polynomial, set p of x equal to 0. It's the first order of business. The second order of business is, if possible, and most likely it will be, if possible, factor. Factor and solve. So then if it's not possible to factor, then you need to use your graphing calculator. So if not possible, if possible, factor and solve. If factoring is not possible, use a graphing calculator or graphing device or something of that sort. So as you start to imagine, graphing polynomials with precision is not that simple. When your zeros aren't whole numbers or integers or rational. Yeah, even if they are rational, it gets very complicated to know how to graph it. Grouping, yes, grouping is a factoring technique. It's one of the factoring techniques, Chen. So let's look at our polynomial. And what is our polynomial? X cubed plus 3x squared minus 4x minus 12. So what are we going to do first? We're going to say, so let me just write p of x again here. P of x is what? X cubed plus 3x squared minus 4x minus 12. So what am I going to do? I want to find the zeros, right? Find zeros. So I'm going to say x cubed plus 3x squared minus 4x minus 12. This equals 0. So now, remember, this is a cubic polynomial. It has 4 terms in it. So Chen brought up grouping. That's exactly what we have to do for this, right? We have to group it. So when we group it, we group the first 2 and the last 2, and we factor out the greatest common factor for each of those 2 groups. And so this here, we got x squared. This is x plus 3. And the next group, we have negative 4 factoring out, and this is x plus 3 as well. Equals 0. We can factor out the x plus 3 from both terms. And I'm left with x squared minus 4. And I don't know if you noticed, guys, this was one of the problems on your exam. If you remember, it was like the first part is the last problem of the first part of the exam. And it says to factor completely. And I saw in some of your test papers, A lot of people did this. But remember, it's factor completely. And what do you notice about x squared minus 4? Right. There's a difference in perfect squares, so you can further factor. So this is x plus 3, x plus 2, x minus 2 equals 0. And then what do we do? Boom, 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 right? And we know what? X equals negative 3, x equals negative 2, and x equals 2. These are all the zeros. We got them. So then we write it up here. What are the zeros? So I usually write them as a set. So the zeros are the negative 3, negative 2, and 2. Those are my zeros. Okay, so we were able to find the zeros because this polynomial was very nice in being able to be factored. And after we factored, we're able to find the factors. And based upon the factors, we're able to figure out the zeros. Now the question becomes, the final task or the final goal, the final objective of polynomials is being able to sketch it. We just want to sketch it. Nothing exactly this exact, but we want a good sketch. And what do we need? We need to plot the zeros. If it is not a perfect square, do we leave it like that? Well, if it's like x squared minus 6, for example, you can still find the zeros. You can still, the whole point, Jen, is to find the zeros. So you can still set x squared minus 6, for example. That's not a perfect square. You can set it equal to 0, and you can still find that x will be square root of 6 and negative square root of 6. But that's the problem, right? When we get those kind of values that are not that nice in terms of whole numbers or integers. So this is an example where the zeros are all very nice, wholesome integers, because then we're able to plot them. That's the whole point. We want to plot them. So if we want to plot them, you know what? I'm gonna expand this a bit. Every two, I'm gonna make it into a every two boxes. Every two boxes is 1 unit. So just to space things out. Okay. So remember, the zeros are what? They're also considered the x-intercepts. So the x-intercepts are going to be where? A negative 3. Where else? Negative 2. And where else? At 2. Those are my x-intercepts. I know them for a fact. Now, how does end behavior fit in all of this? Well, end behavior is going to tell us that no matter what happens in the middle, remember no matter what happens in the middle, what do we know for a fact? As x goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to negative infinity. So for a fact, I must have something that like this. This goes up as you go to the right, and this goes down as you move to the left. This has to happen. This has to happen, right? Then we have to take care of how things look in between with the zeros. And there's one extra thing I feel like I missed here. I have to use the end behavior. And then, you know what also would help, just to give us a little more orientation? They call them test points. It's just to give us other points. And in particular, one of those test points that will be very helpful is the y-intercept. So what is the y-intercept again? Well, that's when x equals 0, right? And if you plug in 0 to our function, what is p of 0? If I plug in 0 into my function, what's the result? Negative 12. So the constant term actually gives us the y-intercept. Oh, wow. That's cool. Okay, so the problem is negative 12 is all the way down here somewhere, okay? So the sketch is going to look a little strange if I were to include it. But the whole point is it's somewhere here, right? Negative 12. So I know I have to cross it here somewhere. So now, what do we do, guys, to give a sketch, just a sketch? So the way I think about it is this. I know how the story ends, right? I know this must go up here. I know this must go down here. And what else do I know? I know that the graph must go through these 3 points. So think about sketching the graph of polynomial as like putting a needle, no, not a needle. What's that thing for the needle? Like putting a string. Like you're trying to put a string through all of these points. A thread. There we go. Thank you, Sydney. That's I was losing my yeah. It's a needle. The thread in the there we go. I can't believe I forgot. Threading the needle. That's when you play basketball, you thread the needle. Anyways, so you're putting a thread through these openings. And there's no funny business. It's a smooth curve. And it has to go through these points and it has to go through this point here. And the only way that's possible is if you draw it this way. This has to go through, right? It has to go through. And then it has to come back somewhere. I don't know exactly where, but it has to come back through this. It has to. And then it has to go all the way down here. It goes through here. And then it has to go through here. And then it continues on. Of course, this is not exactly what happens, but this is the sketch. I have the sketch. I know the end behavior, and that's what it is. To the right, upward, to the left, downward. I know that it has to go through these 3 points, and I know this is going to be the y-intercept. Okay, is this clear? So I'm just going to write this, right? It's good to label what you have. The key points here. Okay. Look at this. Beautiful. We have all the information we need for this one polynomial. This is all the stuff. We're basically becoming very good at just scanning polynomials and get all the information we need. And boom, we have it. So I just want to sketch this and see how good our sketch is actually to the real thing. So what is it? X cubed. And it's plus 3x squared. Whoa. Hold on. So we got x cubed. Whoops. X cubed plus 3x squared minus 4x. And you can put this in your calculators as well, just to give you an idea. And look what I got. It kind of looks like it, right? A little bit. What's the important parts, though? Oh, and also, I forgot to mention, they're also called roots. So the zeros are also called roots. Like we can add that to the to that list, to that equation that we have. So they're roots, right? Sorry, my computer was about to die, so charging it. Okay, good. So we're good. So these are the roots: 2, -2, -3. What's my y-intercept? -12. But the point is that the end behavior to the left goes downward, to the right goes upward, and this is my sketch. Well, this is the actual graph, but my sketch looks very similar, somewhat to it, right? Okay. Cool. You see that? Well, yeah, it's not the greatest sketch, but we're right there. Okay. Makes sense? We're good with this? Okay, good. So now let's look at this next example. Now this should be a little faster. Degree of polynomial. Oh, wait, hold on. Yeah. So when we have something like this, can anyone tell me what the degree of the polynomial will be? It's not that apparent anymore because this is in factored form. This is when you have a polynomial and it's factored. So how do we determine the degree of the polynomial? Right, it's 4. How come? How do you guys know that? How do you know that? Yeah, it's about the x's, right? So we know that if we were to expand everything, right, there's only 4 x's to multiply together. So the result will be x to the 4th. That's the reason why. So we're not going to actually expand everything because that's going to take a long time. But we just already know, we anticipate that if we were to do so, there's only 4 x's that will be multiplied to one another eventually. So that it means that the highest power would have to be 4. And so that means because it's 4, the degree is even. What's the name of the polynomial? It's a quartic polynomial because the highest degree is 4. Now, what's the leading term? What's the leading term? There's also a little tricky one here. Does anybody have a good idea? So you have to be careful with this. There's an x, there's an x, there's an x, but there's a negative x. So when you multiply x, 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 and negative x, exactly, very good, you get negative x to the 4th. It's going to be negative. So you have to be careful with that. It's negative because we have one of those being negative x's. And when we multiply them, you get negative. Okay? And then the leading coefficient will be -1. It's going to be a negative leading coefficient. So then immediately, what do we have? Immediately, we know the end behavior. We know it. And the constant term here, what's the constant term? Oh, that's a good one. What's the constant term? You see, when we have it in factored form, things slow down a bit, actually. Now, remember what we talked about the constant term? It's related to what? The y-intercept? And the y-intercept is related to what being equal to 0? When x equals 0. So to figure out the constant term, all we have to do is plug in x equals 0. So it's p of 0. What happens when you plug in 0 into p? You get 0 multiplied by a whole bunch of other things. So the constant term is 0. So don't forget that, guys. That's kind of an important point here that's glossed over a lot. The constant term is when the x value equals 0, when you plug it in to your function. And whatever the result is, that will be your constant term. Okay? And so then, based upon our end behavior, our degree being even, and our negative coefficient, leading coefficient being negative, then we have something that looks like what? Negative x squared, and then we know that this is as infinity, this goes to negative infinity, as negative infinity, this goes to negative infinity. Done. The y-intercept, remember, comes from the constant term. So we know the y-intercept is 0, 0. We know that because of the constant term. So it's because of this. Now, what are the zeros? What are the zeros? The good thing about something being factored for you is you have the factors. And if you have the factors, the zeros come quite quickly right after that. So we can set it equal to 0. And we don't have to factor because it's already factored for us. So when x is a factor, x equals 0 is the solution, the root, or the 0. Then we have x equals -1, we got x equals 1, and we got x equals 2. So what do we have? We have 4 zeros. Again, what are the zeros also known as? They're also known as the x-intercepts or the roots, right? So again, I'm going to plot this, right? I'm going to put this as -1 just to spread things out a bit. And what do I know? I know that for a fact, we got 2, we got 1, we got -1, and we got 0. Wow, we have all these zeros bunched up together, one after the other. What else do we know? So that's the first thing, right? We plot them. Boom, check. The next thing we know is that the end behavior. What's the end behavior? The end behavior is what? -infinity. So it must go down here to -infinity, and it must go down here to -infinity. We know how it ends. And now think again about the thread and the needle, but in this case, we have 4 openings for the needle that has to go through all of them. So the only way that's possible, right? The only way that's possible is if I draw what? I draw this through here, then it has to come back somewhere, and then it goes through, and it has to come back somewhere, and then it goes through, and it has to come back somewhere, and then it goes right through, and then we get something of this sort. Again, the key word here, sketch. And when we care about the sketch, we care really about 2 things. We care about the x-intercepts, and we care about the end behavior. Yeah, you can think of them as little hills, right? And a valley here. And again, polynomials are very smooth functions, so there's no like pointy precipice. There's no pointiness to it. It's usually very smooth and connected. Right? So let me just give you a sketch as well for this. Again, you can graph this on your calculator as well. So we got x, and then we multiply it by x plus 1. And then we multiply it by x minus 1. And then we multiply it by 2 minus x. Boom. And this is what we got. Of course, my hills are a little bit more pronounced than the actual graph. The actual graph looks much more symmetric than mine. And the hills and the valleys are less pronounced. But again, what do we care about? End behavior. They both point downward. What do we care about? The zeros or the roots. -1, 0, 1, and a 2. Cool. So we're able to give a decent sketch, maybe not the greatest, but a decent one. So any questions about this? Are we all following this? Everything's all right? Everything's good? Okay. No questions about this? I'm glad. Cool. All right. All right. So now we're going to get into the cool stuff. I think so there's going to be now this term, multiplicities. Now we're going to get a little bit more particular with the zeros, because the zeros will not always be this simple. In other words, the factors of the zeros will not always be so simple as the ones we've seen already. And hopefully you see this with this example here. You see what I mean? So what's the degree of the polynomial? This should be quick. 3. This is odd. This is a cubic. The leading term is x cubed. This is the leading coefficient is 1. It's positive. The constant term is -8. It's the same thing as x cubed. This goes to infinity, infinity, negative infinity, negative infinity. What is the y-intercept? Well, the y-intercept is exactly -8 or 0 comma -8 because that's the constant term. Now, what are the zeros? So what are the zeros? Remember what we have to do. We have to set the polynomial. We have to set the polynomial equal to 0. And then we group, right? We group it. So when we group this, what do we get? We get x squared, x plus 2, minus 4 times x plus 2, right? Equals 0. And we get the same thing. We get x plus 2, parentheses, x squared minus 4, equals 0. And then we get x plus 2, x plus 2, x minus 2 equals 0, correct? Now, what's the difference with this example compared to the other ones? Does anybody see something striking about this? Right. You have x plus 2, the factor, associated with the root of x equals -2. It's repeated. That is interesting. So that's really the new piece of information we have. We're like, wait a minute. I got 2 of the same factors. How is that going to influence the graph? So let's see what happens. We know x equals 2, and we know that x equals -2. We know that these two are the roots, right? Are the zeros. But there's a difference in the nature of these zeros. This has a repeated factor. So actually, we can actually write this as the following. We can write this as x plus 2 squared as the factor. And this is going to be x minus 2. So these are my factors, right? Because of this, x plus 2 times x plus 2 is x plus 2 squared. Because it's squared, we call this a multiplicity of 2. Multiplicity, multiple. It repeats twice. So it's a multiplicity of 2. And also, they call it an even multiplicity. And what do you notice about x minus 2? X minus 2 only has a 1 into it. So we don't really say multiplicity of 1 because it doesn't repeat more than once. It's just one time. But the moment your factor repeats, then you have a multiplicity. So in this problem, x minus 2, x equals -2, comes from a factor that is repeated twice. And therefore, this 0 has a multiplicity of 2. It appears twice. So then my x-intercept here, my zeros are -2 and 2, but this has a multiplicity of 2. So then how does that affect my graph, if at all? I know my zeros are what, -2? So I'm going to put this -1, -2, right? Let me see, 1, 2. Yeah, so actually, let's make this by ones. 3, 4, 5, 6, 7, 8. So this is -8, right? Why do I care about that? Because this is exactly where the y-intercept is. And then I got 1, 2, right? And this is 2. So I know for a fact that the graph must go through these 3 points. What else do I know? So I got that part. What else do I know? The end behavior. What's the end behavior? It's similar to x cubed. So what else do I know? I know that this must go up when I move to the right, and this must go down when I move to the left. Okay? Now the question is, how do I connect these two ends? How do I connect them? So then normally what would we do? We would say, okay, let's go through this, and this has to go through here, right? It has to go. That's what we would normally do. But what's the problem if I did this? I would have to do what? Because I want to get to this point here, right? I would have to do what? I have to go through this and then come back down sometime. But what's the problem with that? Do I have another zero? I only have 2 zeros. These are the only 2 points based upon what we just did, what we figured out. So it's impossible. It's impossible for me to go through it and then come back down through this so that it goes through this point here. It's impossible. Why is it impossible? Because I only have 2 of them. So then what's the only other way to satisfy these two, this being the x-intercept? Does anybody know how can I satisfy this? How can I make a graph so that it touches or goes through these 3 points and it goes right through it, and it's smooth, it's connected, and there's no extra zero. There's no extra x-intercept. So the only way it's possible, the only way, is if it does what? If it touches it but never goes through. It bounces back, as they say. That's the only way. That's the only way. So that's important, guys. When you have a multiplicity, in particular an even multiplicity, the root, the graph, bounces. So at an even multiplicity, for zeros with even multiplicity, the graph does not go through, but instead quote unquote, bounces back. Okay, that's pretty important, guys. That's pretty important. When you have a repeated factor and it's an even number of times, when you graph it, it's going to bounce. Whoops. It's going to bounce. And then if you have an odd multiplicity, it goes through. So that's going to be the way to interpret multiplicity now. If you have an even multiple, a factor with an even multiplicity, a 0 with an even multiplicity, you bounce at that point. And if you have an odd multiplicity, you go through. Does that make sense? Does this make sense to everybody, this whole idea of bouncing? I think the last one, yeah, the last one we can probably see if we can go through this real quick. But that's what's gonna look like. Let's see if we can do this next one real quick. And then we'll be done for today. So what's the degree of this polynomial? So if you look at all the x's, right? We got x cubed, we got x, but this x is being squared. So one way to really just find it really quick is just to add up all the exponents associated with x's. So this is 1, right? This is 2, this is 1, this is 3, so it's going to be 6. So degree is 6, is even. The name is a 6th degree polynomial. The leading term is going to be what? X to the 6th. The leading coefficient is 1. This is positive. The constant term. So what's a constant term? When you plug in 0, right? If you plug in 0, p of 0, you get 0 again. So it's 0. So the y-intercept is 0, 0. So this is x to the 6th, looks like x squared. Goes to infinity, negative infinity, goes to infinity. Now what are the zeros? X cubed, x plus 2, x minus 3 squared equals 0. Well, the zeros are quick to get, right? X equals 3 is a 0, x equals negative 2 is a 0, and x equals 0 is a 0. But now what do we care about? We care about the multiplicities. What's the multiplicity here? This is multiplicity of 3. This has a multiplicity of 2. This is even. This is odd. This only appears once. So then what do we know? We know negative 2 at 0 and at 3. 1, 2, 3. We know that at these points, boom, right here and right here, it has to cross, right? We know the end behavior looks like this. Goes up, goes up. And now let's connect it. Oh yeah, and what are the zeros here? I forgot to mention here. X is equal to negative 2, 0, and 3. So then, sketch. What happens though? At negative 2, what happens? It goes through, doesn't it? Doesn't it go through? Because it's just straightforward, right? It has a multiplicity of 1, you can say. It only appears once. What happens at 0 though? What happens at 0? We have a multiplicity of 3. Now the interesting thing is that around this point, right, it does go through, right? It does go through, but it goes through kind of like x cubed would go through because of the cube nature of it. But it goes through regardless, right? Now what happens here at 3? What do we know about at 3? The multiplicity is what? Even. So what do we know at even multiplicities? We bounce. And that would be the sketch for this. Okay. I know we kind of sped through this one, but does that make sense? Okay, we're good with this.